Picture this, a weapon that crosses entire continents in the time it takes you to finish your morning coffee. Just a streak of fire tearing through the upper atmosphere, leaving nothing but a shattered sonic boom in its wake. Welcome to today's Explainer. We've got an urgent, highly detailed briefing on a mission to decode a literal paradigm-shifting breakthrough, one that is fundamentally rewriting the laws of aerospace engineering as we know it. So how exactly do you stop a vehicle that makes every single modern air defense system instantly obsolete, right? That's the exact question military strategists globally are suddenly staring down. For decades, achieving sustained powered flight at Mach 6, we're talking over 4,500 miles per hour, was the impossible dream. It was this brutal frontier that humbled the absolute greatest aerospace powers. But that silence, it just got spectacularly shattered. Just look at this headline for a moment from South China Morning Post. This is the news behind today's video. China conducts ground tests of hypersonic ramjet that can change shape in flight. The graphite seal used in the Chinese breakthrough is the same one the US defense industry desperately needs. With that said, let's go straight to the intro. The algorithm buries channels that show the truth like mine every single day. The only thing that fights back is you. One like, one subscribe, turn on the bell icon. That's how the truth about China survives on YouTube. Don't let it disappear. Thank you very much. Chapter 1. The Hypersonic Propulsion Gap. To truly grasp why this development is such a total revolution, we first have to look at the primary enemy of high-speed flight: physics itself. Traditional jet engines, they're fantastic at a steady pace, but once they hit Mach 3, the extreme friction and pressure literally melts their internal titanium blades. No way around it. To go faster, you need a ramjet. But here's the catch. A ramjet is kind of like a sprinter who can't start from a standstill. It needs a massive, heavy rocket booster just to get moving fast enough to ignite the air flowing through it. Because of this 50-year propulsion gap, designers have historically been forced to bolt two completely different engines together. The result? Heavy, clunky, and honestly, highly vulnerable hybrid systems. And even if you manage to get a hypersonic scramjet moving, keeping a stable flame at those supersonic speeds is incredibly difficult. If you don't manage the internal pressure perfectly, you risk what's known as thermal choking. This is the ultimate villain in hypersonic design. It's basically a critical aerodynamic failure where excessive heat release pushes violent shock waves right back out of the engine's inlet. In just a fraction of a second, it kills the engine, leading to a catastrophic unstart mid-flight. Boom! Game over. Chapter 2. Anatomy of a living engine. For years, this physics trap seemed completely inescapable, but a team of scientists from the Chinese Academy of Sciences and Northwestern Polytechnical University decided to just throw Western aerodynamic conventions completely out the window. Led by visionary engineer Shu Jianzhang, this team asked a really pivotal question. Why settle for two when you can create one perfect machine? And after decades of incredibly patient research, they successfully built the Contra-Rotary Ramjet engine. Guys, this is widely considered the holy grail of single architecture propulsion. It's one cohesive system capable of accelerating from a dead stop on a runway all the way past Mach 6, completely eliminating those risky mid-flight engine handovers. So how does it actually defeat physics? Well, instead of using multiple stages of compressor blades spinning in just one direction, this radical design uses two sets of blades spinning in opposite directions. This contra-rotatory motion creates a massive compression effect in an astonishingly tiny space, effectively doing the work of 6 standard stages with just 2. Plus, normally in aerospace engineering, shock waves are a violent hazard that will literally rip an engine apart. But this system, it actually uses shock waves as a free tool to further compress incoming air, boosting combustion efficiency to unprecedented, almost impossible levels. But the real genius here is the sheer adaptability of the design. This engine is practically alive. Remember that catastrophic thermal choking we just talked about? To prevent that, this engine dynamically morphs its internal, biological-like throat geometry in just 0.33 seconds. Whether the vehicle is cruising at Mach 1.8 or screaming through the sky at Mach 6, it instantly tightens and relaxes its internal architecture to maintain the absolute perfect flame at any speed. It's constantly breathing, constantly adjusting. Chapter 3. Surviving Superheated Plasma. Now, this morphing ability introduces the next immense challenge, surviving the punishing friction of the atmosphere itself. When you're traveling at Mach 6, the air rushing inside this engine isn't just moving fast, it becomes a superheated plasma. We're talking stagnation temperatures hitting 1,650 degrees Celsius. To put that into perspective, a temperature that high would cause traditional metal seals to simply vaporize instantly. Poof, gone, allowing superheated gases to flood and destroy the delicate internal mechanics. Their solution to this is an absolute masterclass in extreme material science. The engineering team created a massive breakthrough using high-temperature graphite seals. By mastering the exact same black mineral you'd find in a simple pencil, they've engineered seals that provide extreme thermal stability and crucial self-lubrication. This completely protects the delicate, morphing internal mechanical actuators from vaporizing, allowing the engine's geometry to shift smoothly even while completely engulfed in plasma. Unbelievable, right? And the absolutely crucial point when designing these hypersonic vehicles is relentlessly managing mass. Standard advanced superalloys sit at a brutally heavy 8.5 grams per cubic centimeter, but by utilizing advanced carbon-carbon composite materials coming in at an incredibly light 1.7 grams per cubic centimeter, designers cut the weight drastically. Not only are these composites roughly 50% lighter than standard metallic alternatives, but they can miraculously endure temperatures of 3,000 degrees Fahrenheit, all without the need for heavy, complex, active liquid cooling systems. Chapter 4. Tactical Power and Efficiency. This incredible synergy of mechanical engineering and material science brings us out of the lab and into a terrifying tactical reality. Data highlights a vital strategic choice regarding fuel. While liquid hydrogen boasts a massive lower heating value, making it ideal for extreme speeds between Mach 8 and 15, it requires highly complex, really heavy cryogenic storage. So engineers are instead prioritizing easily storable hydrocarbon fuels, like JP-8, for tactical cruise missiles. This means these missiles can be kept in a ready-to-use condition for long periods, operating lethally and effectively in the critical Mach 4 to Mach 8 regime. What this strategic choice means is the era of the unpowered, predictable glide vehicle is officially over. We've entered the era of powered hypersonic cruise. Because the weapon retains an active, burning engine throughout its entire flight path, it can perform aggressive, high-G evasion maneuvers to bypass layered defenses, all without bleeding off any of its blistering speed. And because the single engine is so compact, these weapons can literally be hidden internally within the payload bays of next-generation stealth aircraft. The math on this kill chain is staggering. Firing a powered hypersonic weapon from 3,000 kilometers away leaves the defender with a reaction time of just 98 seconds. Think about that. From the exact moment it appears on a radar screen to the devastating moment of impact, you have less than 2 minutes. In the realm of modern defense strategy, that is an absolute checkmate. Chapter 5. The Next Frontier. But the implications of this single architectural engine stretch far beyond the military domain. The technologies being proven in the skies today are the direct stepping stones to completely transforming global transportation. Beyond tactical missiles and integration into upcoming stealth fighters like the Little Six, thanks to the ability to take off from a conventional runway and rapidly accelerate past Mach 6, we could very soon see commercial, reusable aerospace vehicles capable of flying from Beijing to New York in under 2 hours. Let that sink in. And engineers are already pushing the boundaries even further with magnetohydrodynamic or MHD power generation. This is truly sci-fi stuff that is becoming reality right now. It effectively turns the engine's intense exhaust heat into a massive electrical generator. By extracting electrical energy directly from the hot exhaust gases, the system can channel that power to run heavy-duty onboard sensors and directed energy lasers, while miraculously cooling the engine itself at the exact same time. The impossible barrier of sustained hypersonic flight hasn't just cracked, it has been completely shattered. As this Mach 6 frontier becomes our new reality, we want to know what you think. Based on these massive leaps in single-engine technology, military analysts are now actively asking, is the West officially out of the hypersonic race? Think on that. Thanks for joining us for this explainer. It's been a fascinating journey through the data, and we will see you next time.